Nobody told you the universe was supposed to make sense. Nobody warned you that the most expensive, most powerful, most precisely engineered eye humanity has ever pointed at the sky would come back with an answer that scientists described using one specific word. And that word is not amazing, it is not revolutionary. The word they keep using in peer-reviewed papers, in closed-door briefings, in conversations between Nobel Prize winners, is terrifying. Not metaphorically, not dramatically, literally terrifying. Because what the James Webb Space Telescope has been sending back to Earth is not just data. It is a series of discoveries that are quietly, systematically dismantling every major assumption we have ever made about how the universe works, when it started, and what is actually out there in the dark. And what makes it truly terrifying is not what Webb found. It is what Webb found that should not be there at all. Let that sit for a moment, because this is not a story about space being beautiful. This is a story about space being wrong, or rather, about us being wrong about space. And the difference between those two things is the difference between wonder and crisis. Right now, in the corridors of NASA, in the astrophysics departments of Johns Hopkins, Cambridge, and Caltech, in the late-night emails between the people who built the models that we have relied on for decades, there's a quiet, controlled, professionally worded panic. Because the James Webb Space Telescope did not confirm what we thought we knew. It obliterated it. Discovery after discovery, image after image, dataset after dataset, Webb keeps returning the same verdict. Our map of the universe is wrong, and we have no idea what the correct one looks like. This is where we begin. The James Webb Space Telescope launched on Christmas Day, 2021. It took 30 years to build, cost $10 billion, and required the cooperation of NASA, the European Space Agency, and the Canadian Space Agency to bring to life. It was designed to be the most powerful infrared observatory ever constructed, a machine capable of peering so far into the cosmos that it could see light that left its source 13 billion years ago. Light from the very first objects that ever existed after the Big Bang. The scientific community called it a generational leap. They said it would answer questions that Hubble could only dream of asking. They were right, but they made one catastrophic miscalculation. They assumed the answers would confirm the theories they had already built. Instead, the answers started tearing those theories apart, one by one, layer by layer. And the deeper Webb looks, the worse it gets. Here is the first thing you need to understand. Modern cosmology, the science of the universe itself, its origin, its structure, its fate, rests on a framework called the Standard Model of Cosmology, sometimes called Lambda CDM. This model is not a guess. It is the result of a century of observation, mathematics, and verification. It tells us the universe is approximately 8 billion years old. It tells us the universe began with a Big Bang. It tells us that in the first few hundred million years after that event, space was a chaotic, cooling soup of hydrogen and helium slowly being pulled together by gravity into the first primitive structures. Stars came first, then small galaxies. Then over billions and billions of years, through mergers and collisions and the slow accumulation of matter, those small primitive galaxies grew into the massive, complex, structured ones we see today. Galaxies like our own Milky Way. This is the story. This is the model. This is what every textbook, every documentary, every classroom, and every country teaches. And this is exactly what the James Webb Space Telescope just told us is fundamentally, profoundly, perhaps irreparably broken. Because Webb looked into the deep, early universe, into the period just a few 100 million years after the Big Bang, precisely where the model predicts there should be nothing but chaos and primitive infant structures, and found something that should not exist. It found enormous, fully formed, spectacularly massive galaxies. Not small ones, not primitive ones. Fully evolved, mature, structured galaxies with billions of stars already in place, already organized, already ancient by the time they should have barely begun to form. In 2023, researchers analyzing Webb data identified 6 candidate galaxies from the early universe, some of which appeared to contain as many stars as our entire Milky Way. Our galaxy took over 10 billion years to assemble. These objects appear to have done it in a fraction of that time. The researchers described the finding using a word that almost never appears in scientific literature unless something has gone very wrong. They called these galaxies impossible. Read that again. Not surprising, not unexpected. Impossible. Dr. Ivo Laba of Swinburne University, one of the lead authors of that study published in the journal Nature, said publicly that if these findings are confirmed, they are, quote, a crisis for cosmology, because a crisis is not a problem you solve by tweaking the model. A crisis is what happens when the data and the model are so fundamentally incompatible that one of them has to be wrong. And the data is coming from the most precise telescope humanity has ever built. So the uncomfortable, career-defining field reshaping question becomes, is it the model that is wrong? And if the model is wrong, if the standard model of cosmology is broken, then everything built on top of it is built on sand. Our understanding of how galaxies form, how dark matter behaves, when the first stars ignited, how the universe evolved, all of it, potentially, in need of a complete rewrite. But here is where it gets worse. The impossible galaxies are only one thread of the unraveling. Because while Webb was finding structures that should not exist this early in cosmic history, it was simultaneously confirming something that physicists had been quietly arguing about for years, something that had been dismissed by some as a measurement error, something that others had been trying desperately to explain away, and now can no longer. It is called the Hubble tension, and it is, without exaggeration, the most significant unresolved crisis in modern physics. Here is what the Hubble tension is. The universe is expanding. We have known this since Edwin Hubble confirmed it in the 1920s. The rate at which it expands is described by a number called the Hubble constant. For decades, there were two main ways to measure this number. The first method looks at the cosmic microwave background, the faint afterglow of the Big Bang. Light that has been traveling since the universe was only 380,000 years old. Using this ancient light and the best mathematical models of how the universe evolved, scientists calculate that the Hubble constant should be around 67 kilometers per second per megaparsec. The second method looks at the local universe, at stars called Cepheid variables, and exploding stars called type Ie supernovae, which act as reliable distance markers, and measures the expansion rate directly. That method consistently comes back with a number around 73 kilometers per second per megaparsec. Two different measurements, two different numbers, a discrepancy of roughly 8%. 8% sounds small. It is not small. In the language of physics, this discrepancy is catastrophic. For years, scientists hoped it was a measurement error. Maybe one method was slightly off. Maybe the instruments were imperfect. Maybe there was a systematic bias somewhere in the data collection. So they refined the measurements. They built better instruments. They ran the calculations again and again. And then, in 2023, the James Webb Space Telescope entered the picture. And instead of resolving the tension, it made it worse. Webb observed over 1,000 Cepheid stars across multiple galaxies, producing by far the most precise and comprehensive measurement of the local expansion rate ever conducted. The result, published in the Astrophysical Journal Letters, and led by Nobel Prize-winning physicist Adam Rees of Johns Hopkins University, was unambiguous. The local measurement of 73 was correct. The discrepancy was real. There was no measurement error. There is something wrong with our understanding of the universe itself. Adam Rees said it plainly. He said, quote, "What remains is the real and exciting possibility we have misunderstood the universe." Exciting, he said. Think about what it means for a Nobel Prize winner to use the word exciting when he is telling you that everything physicists have built for the last 50 years might be fundamentally wrong. It means he is trying very hard not to say the other word. The word that David Gross, another Nobel Prize winner, used at a major physics conference, the word Gross used was not problem. It was not anomaly. It was crisis. A crisis in cosmology, he said. And a crisis in cosmology is a crisis in everything, because cosmology is not a narrow field. It is the field that contains all other fields. It is the study of everything that exists. So what could explain it? What could cause the universe to appear to be expanding at two different speeds depending on how you measure it? Physicists have proposals. Some suggest there may be a form of dark energy that we do not currently understand, an energy embedded in the fabric of space itself that may not be constant across time, that may have behaved differently in the early universe than it does today. Others suggest there could be new unknown particles that existed briefly in the early cosmos and provided an extra kick to cosmic expansion before disappearing. Some theorists have proposed something called early dark energy, a transient burst of energy density that briefly dominated the universe shortly after the Big Bang and then faded, leaving behind an expansion rate permanently higher than models predict. And then there are those who say something even more unsettling, that Einstein's theory of general relativity, the foundational framework of modern physics, may not work perfectly at cosmic scales. That one of the most tested, most verified, most relied upon theories in all of science may need to be modified or replaced. And this is where everything changes, because the James Webb Space Telescope is not just observing distant galaxies and measuring expansion rates. It has been doing something else, something that the headlines have mostly missed, something that scientists are still trying to process in real time. Webb has been staring into the deepest, darkest corners of the early universe and finding structures that challenge not just our models of galaxy formation, but our understanding of time itself In early 2026, Webb broke its own record, again by confirming the most distant galaxy ever observed, a galaxy called MZ14, visible as it appeared just 280 million years after the Big Bang. Let that number sink in. 280 million years. In cosmic terms, that is barely an instant after creation. And yet, there it was, a galaxy, not a cloud of gas, not a scattering of primitive stars, a galaxy with all the structural complexity that word implies, already in existence, already glowing, already far more developed than it had any right to be. What most people are not seeing is that each record Webb breaks makes the problem worse, not better. Because every time we find a galaxy earlier in cosmic history than we expected, it means galaxies were forming faster than the model predicts. And if they were forming faster, something was driving that formation, something we do not have in the equations, something we have not accounted for. And right now, no one knows what it is. But let us go deeper. Because the impossible galaxies and the Hubble tension are what scientists talk about in papers and conferences. There is something else emerging from Webb's data that is talked about in quieter rooms and mentioned almost in passing, because it is the kind of discovery that, if fully confirmed, does not just challenge a model, it challenges the human impulse to believe we understand our place in the universe at all. It concerns the Great Filter, and the implications are existential in the most literal sense of that word. The Great Filter is a concept from a framework called the Fermi Paradox. The Fermi Paradox asks a deceptively simple question. If the universe is enormous, ancient, and filled with the chemical ingredients for life, where is everyone? Where are the signs of other civilizations? Where is the radio traffic, the megastructures, the signals we would expect from even one other intelligent species that had a billion-year head start on us? The silence is profound. And the Great Filter is one possible explanation. It suggests that somewhere in the chain from simple chemistry to complex life to civilization, there is a filter, an obstacle so devastating that almost nothing gets through it. Almost nothing survives it. The terrifying question is where that filter sits on the timeline. Is it behind us? Something we have already passed? Something that killed off most life before it reached our level of complexity? Or is it ahead of us, waiting? And here is what Webb has done to that question. Webb has been examining the atmospheres of exoplanets, planets orbiting distant stars, with a precision never before possible. It has already detected carbon dioxide in the atmosphere of a planet 700 light-years away. It has probed the atmosphere of TRAPPIST-1d, a rocky, Earth-sized planet sitting in the so-called habitable zone of its star, the zone where liquid water could theoretically exist on a planet's surface, and found that it does not have an Earth-like atmosphere. The finding was released in 2024. TRAPPIST-1d was one of the most promising candidates for habitability we knew of, and Webb looked at it and found nothing resembling what life would need. Think about what that means. One of the best candidates we had, gone. Not because the planet is hostile, but because it apparently never developed the kind of atmosphere that sustains life as we know it. And as Webb continues to examine these worlds, as it builds up a body of data on the atmospheres of the most promising planets in the galaxy, what that data is starting to suggest is not that life is everywhere, and we simply cannot detect it. What it is starting to suggest is that the conditions for life, even basic microbial life, may be far rarer than our most pessimistic models predicted, which brings the Great Filter back into focus, not as philosophy, as data. Because if planet after planet, even the most promising ones, shows no signs of the atmospheric chemistry associated with biology, if the universe turns out to be vast and ancient and overwhelmingly profoundly sterile, then the filter is either behind us or directly in our path. And neither answer is comfortable. But here's the piece that connects everything: the impossible galaxies, the broken expansion rate, the sterile exoplanet atmospheres. There's a thread running through all of them, and when you see it, you cannot unsee it. Every one of these discoveries points to the same underlying conclusion. Our models of how the universe works, how it began, how it evolved, how it creates and sustains complexity, are wrong in ways that are not yet understood. And the reason that is terrifying is not because wrong models are unusual. Science is full of models being replaced by better ones. That is how science works. The reason it is terrifying is the timing, because the James Webb Space Telescope was built to answer the deepest questions humanity has ever asked. And instead of answering them, it is revealing that the questions themselves may have been built on a foundation we never properly tested. Consider the scale of what is at stake. The lambda CDM model, the standard model of cosmology, is the framework on which decades of scientific funding, research programs, university curricula, and theoretical physics have been constructed. It is the lens through which we interpret every observation of the universe. Every telescope, every satellite, every calculation depends on it. If it breaks, not in a small patchable way, but in a fundamental structural way, then the field does not just need a revision, it needs a reconstruction. And reconstructions take generations. According to informed sources within the astrophysics community, the conversation happening right now is not whether the standard model needs adjustment. It is how deep the adjustments need to go. Some researchers believe the solution is relatively contained, perhaps a new form of dark energy, perhaps early dark energy, perhaps some exotic particle physics in the first moments after the Big Bang. Others are less optimistic. Some believe the discrepancies Webb is revealing point to something much more radical, that the geometry of the universe is not what we think, that dark matter behaves in ways fundamentally different from our assumptions, that the very concept of cosmic time may need to be reconsidered. These are not fringe positions. These are being published in Nature, in physical review letters, in the Astrophysical Journal, by Nobel laureates, by the people who built the models in the first place. And then there's the issue that nobody in mainstream coverage is talking about loudly enough. The James Webb Space Telescope may go dark, not metaphorically, literally. In April 2025, reports emerged that the telescope, this $10 billion machine, this once-in-a-generation instrument, the most powerful scientific tool humanity has ever deployed, was facing potential operational disruptions due to funding, pressures, and administrative changes within NASA's scientific programs. The telescope that is in the middle of rewriting cosmology, that is in the middle of answering, or rather demolishing the answers to the deepest questions we have ever asked, is not guaranteed to keep operating. In a moment when what we need most is more data, more observation time, more years of Webb staring into the dark and sending back its incomprehensible findings, the machine itself is under threat. And if Webb goes silent before we fully understand what it has already found, we will be left holding a map that tells us our old map is wrong, without enough information to draw a new one. What the real story is, and what most people are not seeing, is that we are living through a scientific inflection point of a kind that happens perhaps once in a century. The last time cosmology faced a crisis of this magnitude was in 1998, when the discovery of dark energy, yet the realization that the universe's expansion was not slowing down but accelerating, shattered the prevailing model and earned the scientists who found it a Nobel Prize. That discovery required a new ingredient to be added to the cosmic recipe: dark energy, this mysterious force that makes up approximately 68% of the total energy content of the universe, a force we can measure, but cannot identify, cannot explain, and cannot directly observe. We simply know it is there because of what the universe is doing. We named it, we quantified it, we inserted it into the equations, and we moved on, as if naming something were the same as understanding it. Webb is now suggesting that even our understanding of dark energy may be wrong, that it may not be a constant, that it may have varied over cosmic time, that the universe, in other words, has been playing by rules that change. And if the rules change, then the predictions we make from those rules, predictions about the universe's fate, about its age, about the nature of space-time itself, may all need to be reconsidered from the ground up. There is a specific phrase that keeps appearing in the scientific literature generated by Webb's findings. That phrase is tensions with the standard model. It appears in paper after paper, in study after study, and scientists reading those papers understand that tensions is the professional, measured, peer-review-friendly way of saying something is deeply structurally wrong. Because individual tensions are not unusual, one tension can be a measurement error. Two tensions can be coincidence, but when tension after tension after tension emerges from a single telescope pointing at a single universe, when the impossible galaxies and the broken Hubble constant and the sterile exoplanets and the dormant galaxies and the impossibly early structures all point in the same direction, you are no longer dealing with noise, you are dealing with a signal. And the signal is telling you that the universe is not what you thought it was. Astronomers using Webb in January 2026 found something dubbed JWST's quintet, a collision of at least 5 galaxies interacting in a compact region of space just 800 million years after the Big Bang, far earlier than any model predicted such complex galactic interactions could occur. The system was surrounded by oxygen-rich gas, oxygen, an element produced by stellar fusion, which requires stars to have lived and died, meaning stars had already completed entire life cycles, billions of them, far earlier than the timeline allows. The researchers were clear. This was not expected. Before Webb, astronomers assumed complex galaxy mergers and the widespread distribution of heavy elements would not become common until well over 1 billion years after the Big Bang. Webb found them at 800 million years. And each time Webb finds something like this, the gap between what the model predicts and what the universe actually contains grows wider. Meanwhile, the little red dots, mysterious, small, intensely bright objects first spotted by Webb in the earliest eras of the universe, continue to resist classification. By mid-2025, astronomers had compiled a massive catalog of them, all dating back to the first one, 5 billion years of cosmic history, and found that a large proportion appeared to contain supermassive black holes that were actively growing. Supermassive black holes at the hearts of nascent galaxies, already billions of times the mass of our Sun, already feeding, already dominant, in an era when the universe was too young by conventional timelines for objects of that scale to have formed. Some researchers have proposed these are a new class of galaxy entirely. Others suggest they represent a phase of star formation so intense and so rapid that our models simply do not have a mechanism to explain it. Nobody fully knows. And in science, when nobody fully knows, that is not the end of the story. That is the beginning of the crisis. According to data compiled through 2025, Webb has now confirmed measurements that rule out a simple measurement error as the source of the Hubble tension with what scientists call very high statistical confidence. The language of ruling out with confidence is the language of finality. It is scientists saying, we checked again, we checked with the best instrument ever built. The answer is the same. The universe is expanding faster than it should be. Something is wrong, and we do not know what. There is something philosophically vertiginous about this moment in human history. We built a machine to see the beginning of time. We spent 30 years and $10 billion and the careers of thousands of scientists to construct this instrument, to launch it perfectly, to unfold it flawlessly in the cold vacuum of space, to calibrate it with extraordinary precision. And then we pointed it at the universe, and the universe looked back and said, you have been wrong about me, not about the details, not about the minor calculations, about the major things, about how I began, about how I evolved, about what I am made of and how fast I am moving and what is possible within my laws. You have been wrong, and you're only now beginning to understand how deeply wrong you have been. That is the terrifying discovery. Not a black hole, not an asteroid, not a signal from another civilization. The terrifying discovery is the scope of our own ignorance, revealed not by failure, but by success. Webb is working exactly as intended. It is seeing exactly what it was built to see. And what it is seeing is breaking the frameworks that humanity spent a century constructing. The question now is not what Webb will find next. The question is whether we will have the scientific infrastructure, the funding, the operational continuity, the institutional commitment to follow these threads wherever they lead, because they are leading somewhere. The data is not random noise. It is coherent. It is consistent. It is pointing toward something. What that something is, nobody can yet say with certainty. But informed voices in the field, people who have spent their careers mapping the cosmos, are beginning to say, quietly, in careful language, that what is coming may be the most significant revision of scientific understanding since Einstein replaced Newton. Not an update, a transformation, not a refinement of the model, a replacement of it. And perhaps the most unsettling part of all is this. Webb was supposed to be the answer. It was supposed to close the book on the biggest questions in cosmology. Instead, it has opened a door onto a corridor that extends further than we can see, in a direction we did not know existed, full of rooms we have no language yet to describe. Every answer Webb has given us has come with 3 new questions attached. Every observation that resolved one uncertainty has created a deeper one. The universe, it turns out, does not get simpler the more carefully you look. It gets stranger. It gets more complex. It reveals layers of structure and mystery and contradiction that no model, not yet, has successfully accounted for. And there is no one coming to fix this quickly. The theoretical physicists are working. The observational astronomers are working. The data scientists processing Webb's outputs are working around the clock. But scientific revolutions do not happen in press releases. They happen slowly, painfully, through the accumulation of evidence that cannot be ignored until the old framework collapses under its own contradictions, and something new, something nobody has fully imagined yet, takes its place. We are somewhere in the middle of that process right now. We are in the zone of maximum discomfort, where the old answers have been discredited and the new ones have not yet been written. So here is where we are. The James Webb Space Telescope has confirmed that the universe is expanding faster than our best models predict. It has found galaxies so massive and so ancient that they should not exist by the timeline the standard model provides. It has found galaxy mergers and stellar populations and chemical distributions happening hundreds of millions of years earlier than the models allow. It has found black holes at the centers of infant galaxies, already at scales that defy the formation timelines we calculated. It has probed the most promising nearby exoplanets and found atmospheres that do not resemble what life needs. It has, in short, told us that we are more lost than we thought we were, and simultaneously given us the most detailed, most precise, most comprehensive view of the cosmos that any instrument in human history has ever produced. We know more about the universe than we have ever known, and we understand it less than we thought we did. Ask yourself what happens when that telescope goes quiet, when the funding dries up, when the operational window closes, when the greatest eye we have ever opened onto the cosmos shuts, before we have finished reading what it is trying to tell us. Ask yourself what it means to be standing at the threshold of the greatest scientific revolution since Einstein, equipped with the tools to see it clearly and to choose not to look. Ask yourself what the universe is trying to say with all of this, with the impossible galaxies, with the broken expansion rate, with the silence from the exoplanets that were supposed to be our best hope. Because the universe has been here for 8 billion years, or perhaps longer, perhaps much longer, and it has been running by rules that we are only now realizing we never properly understood. And the James Webb Space Telescope, this golden, hexagonal, cold, silent machine floating 1 million miles from Earth in the darkness between here and forever, is still watching, still measuring, still sending back its transmissions, still telling us something, still waiting for us to be smart enough to understand what it is saying. The question is not whether the universe contains answers we have not yet found. The question is whether we are asking the right questions. And the deeper question, the one that keeps physicists awake, the one that haunts the margins of every paper Webb has generated, is whether the right questions are ones we are even capable of forming yet. Whether the human mind, this 3-pound instrument of biology and electricity, is equipped to comprehend what Webb is showing it. Whether what is waiting at the end of this road of discovery is something that will expand human understanding to its greatest limit yet achieved, or something that will reveal, once and for all, just how small that limit has always been. Something is out there. The data is clear. Something is out there that we have not named, have not modeled, have not imagined. Webb can see it. We just cannot yet understand what we are seeing. And what comes next? That is the part nobody is prepared for.